Hi, welcome to the new video here. If you have not watched the solving differential equations video, that should be posted just below this, make sure you do that first, and then you can watch this one afterwards. Because if not, then you're gonna be confused about the steps that we're pulling after this. So what we're going to talk about is applying solving differential equations. So some of you have asked about where we use real-world ones. Some of you come up with some interesting ideas based off of our extending our thinkings done in class. But here's one that's I don't think many of you would have thought of, which is something called a mixing problem. So this can be used when you're mixing together two different solutions to try to create the right amount of, in this particular case, salt, or the right amount of some sort of chemical or alcohol, or really anything where you need the right balance of something. This can also be used to sort of think about bodies. Bodies are just compartments that are mixing things together all the time. So how can you sort of model how blood flows, or how water flows through your intestines, or how things flow through your liver, your lungs. You shouldn't have things flowing through your lungs other than air, I guess. Anyways, so those are really complex because there are a lot of compartments. The one we're going to work on here is much less complex because it's just a single container. So let's read through this. We got a tank. It contains 20 kilograms of salt dissolved in 5,000 liters, I can read, of water. Brine. Brine is a fancy word for salt water. It's also a word that you should know if you like cooking. If you've ever cooked chicken breasts or pork chops and you've thought, man, those are dry and tasteless, here's an idea. Put it in some brine. So salt water with a little bit of honey actually in it. Let it rest for a day. When you cook it nice and juicy. So cooking tip for you. There you go. So salt water or brine that contains 0.03 kilograms of salt per liter enters the tank at a rate of 25 liters per minute. The solution is kept thoroughly mixed, meaning like the salt doesn't fall to the bottom of the tank, and drains from the tank at the same rate. So still at 25 liters per minute. How much salt is in the tank at half an hour? Okay. So some things to sort of note here is that we got three different quantities going on here. So there's kilograms. We got kilograms, 20 kilograms, 0.03 kilograms. We've got liters, 5,000 liters. This is a 25 liters per. And then we've got time, minutes. So there's three different quantities going on here. And so to try to figure out this from like a direct route might be kind of confusing because there are the three different quantities. So we can actually avoid some of that. How do we avoid it? Well, first let's define some variables. I define my variables based off of the question. They want to know how much salt is in the tank after half an hour. Salt and time are really the only things that I care about in my question. I'm not such a fan of liters. Also notes that since the water's flowing in and out at the same rate, the amount of liquid in the tank is always 5,000. So since it's a constant, we can actually not worry about it too much. Which actually means that if we had a changing volume, our approach here might not work. So let's talk about variables. I sort of already preemptively did some stuff here. So I said T is time in minutes. I said then that A is the amount of salt at time T. That's in kilograms, I should clarify. In kilograms. Okay. So how do I go about trying to write an equation here, okay? To try to do a direct route, like I said, it can be a little bit tough. There are a lot of moving pieces here. You got water coming in, you got water leaving, you got salt coming in, you got salt leaving. And something to note is that the concentration of salt is changing. So it goes from being 20 out of 5,000, which, quick math here on my calculator, that's 0.004 kilograms per liter. And we're pumping in at 0.03 kilograms per liter. So this is a much stronger concentrate than what was originally in there. So the amount of salt in the tank is increasing. And as time goes on, we can also think about like, well, what does it increase to? Well, it would start approaching this amount as time goes on. But that's not what the question's asking here. So now we need to sort of think about, well, how do I set up something that would help us out? So we have a lot of information about how things are changing. So that's how we should set up our problem. Our problem should be, what we're interested in is finding A of 30, by the way. So at 30 minutes, what is the amount of salt? So our setup here is as follows. We got dA over dt. In other words, the amount of salt changing with respect to time. Well, that's just how much salt is coming in subtracted by how much salt is coming out. Kind of it seems really simple, but you might not have thought of it at the time here. So like, how much salt is in there? Well, how much came in and how much left, then that gives you how much there is. Oh, 20 came in and 4 left. I got 16. It's not quite that simple, but that's sort of the idea. So we need to come up with expressions that represent the rate in and the rate out. So that's what we're going to do next here. So let's talk about the rate in. So over here I'm going to write out how we figure out rate in. So something to note is that this differential equation, I should pay attention to the units. A has the units of kilograms. T has the units of minutes. So we're thinking about kilograms per minute. So that's what these should be, kilograms per minute, kilograms per minute. So I'm just going to come over here and write next to this, kilograms per minute, as sort of a reminder that like, that's what I should have. So dimensional analysis can help us out here. So how much is coming in? Let's look. Brine is entering the tank, is being pumped into the tank. What is it? Well, we got 0.03 kilograms per liter. Okay, let me write that down. So 0.03 kilograms per liter. All right, and then the actual amount of liquid is 25 liters per minute. Well, I noticed that if I multiply liters per minute by kilograms per liter, I end up with kilograms per minute. So let's do that, 25 liters per minute. So the liters will divide to 1, so that gives us 0.75 kilograms per minute, just as I was expecting. Great. Okay. So that will be the rate in, dA over dt. I'm going to write the rate in as 3/4 as a fraction, just because I like fractions more than I like decimals personally. You might be different. All right, let's talk about the rate out. The rate out is a little less obvious because the rate out depends on us knowing, well, how much salt is in the tank. And as we said before, that amount is changing constantly. So let's think about that. Rate out. Well, one part of the rate out we totally know is going to be the same. It's the 25 liters per minute. So the liquid is pumping out at the same rate it's pumping in. So we know we got 25 liters per minute. That's definitely the same amount. What's unknown for us is how much salt is in the tank. Luckily, we do know how much liquid is always in the tank. We just don't know the amount of salt in there. So how many kilograms of salt, unknown, but hey, I've defined that up here. I've called that A. So I got A kilograms. And that's going to be divided by, well, the amount of liquid that's in the tank. That is always 5,000 liters. So here I have 25 kilograms per liter, liters per minute. The liters still divide to 1, so I'm left with kilograms per minute. But in the thing here is going to be 25A all over 5,000. Which totally simplifies. What does that simplify to? Here we go. 5,000 divided by 25. So that's going to be a 1A over 200. So I'm going to write that out. Minus a over 200. That's what this simplifies to. Okay. That's not so scary to be looking at here. I actually am digging this. So let's see what happens here. So the first thing I'm going to do is I'm going to make this nicer. I don't like the way that it looks. I don't like the way that it smells. It doesn't smell. I'm going to write it as a single fraction. I feel like that's easier for me to deal with here. So dA over dt equals, so what am I going to need to do here? I'm going to need to multiply by, is it 50 here on both sides? So what does that get me? That's going to get me 150 minus a all over 200. Great. So there's my differential equation. And I believe it's ready to be solved. So let's try that out. So I'm going to get all my a's to one side, all my t's to the other. I'm going to move my a's over here since I got dA in the numerator. I'm going to move my t's over to here. And let's see what happens. So multiply by dt to start out with. So that's going to get me dA is equal to 150 minus a over 200 times dt. Okay, still got an a over here, so I'm going to go ahead and move that over. So I'm going to multiply by 1 over 150 minus a. 1 over 150 minus a. So those will divide to 1. So I've got dA over 150 minus a is equal to 1 over 200 dt. You could have also moved the 200 over, but since I'm going to end up solving for a at the end of everything, I'll probably end up moving it over at the end of it, so I just left it there. I only moved over the stuff that only has the a in it. All right, at this point, we can now integrate both sides with respect to their given variables there. So let's see what we get here. So I'll deal with the right side first. It's a little less scary. So a constant, the derivative of a constant, or sorry, the derivative of something that's just a constant, well, it must have been just that constant times the variable. So the derivative of 1 over 200t is 1 over 200. I'm also going to throw down the plus c over here. All right, this other side here. Well, we've talked about this in class. 1 over 150 minus a is what we're dealing with here. So let's see if we find the integral of that, that's going to be a natural log. Oh, but that denominator has a derivative that isn't 1, so it's going to have to be, ooh, maybe we'll do some side work here. Let's take a sidebar and think about the integral of 1 over 150 minus a dA. So if I call the denominator u, its derivative is -1. So du is equal to negative dA. So if I do a substitution here, I get that the integral of 1 over u times -1 du. Nope, check that. Boom. That's what I meant. Negative du equals dA. All right. So then that means that the integral here is going to be the negative of the integral of 1 over u, and so that's negative integral of, sorry, negative natural log of the absolute value of u, plus a constant, but I've dealt with that over here, so I don't have to worry about that. So basically I just did some quick substitution here. But the main reason is That denominator, the inside function, its derivative isn't just 1, so I had to compensate, the negative. So you might not have to do substitution. You might have just noticed that, hey, that should be negative, but it works out. Okay, so let's come back over here. So the integral of this is going to be negative the natural log of, but not u, I'm going to slap back in 150 minus a. Great. All right, next step is to isolate a. So first I'll take care of that negative. So negative 1 over 200t minus c. And now to solve for this, I'll make it e to the power of, so I'll exponentiate both sides with the power of e. So that'll be the absolute value of 150 minus a is equal to e to the negative 1 over 200t plus a constant, minus a constant. That's a minus sign. Minus. Let me fix that. There we go. Okay. And then plus or minus, that undoes the absolute value, so plus or minus e to the negative 1 over 200t minus c. Subtract over 150, so negative 150 plus or minus e to the negative 1 over 200 t minus c. And now the negative there, so a is equivalent to 150. Since it's plus or minus, when you undo that, it's minus or plus, it doesn't matter. E to the negative 1 over 200t minus c. All right, there is your formula. Okay. So now, what do we need to do here? Well, now we're going to need to think about the plus or minus. I don't think it's always plus or minus. I think the plus or minus, it's either positive or it's negative here. So let's think about that as we move forward here. Which one makes sense? Which one? Well, so is the salt in the tank always going to be more than or less than 150? Okay, well this is where we can think about the original amount of salt in the actual tank, because if the original amount of salt was less than 150, then guess what? The amount of salt must always be less than 150. But if it started out as more, well then this should be more. So if we look back at the original problem, it says that there was 20 kilograms at the start of everything. And it's increasing. So that would mean that the salt is going to be always less than 150. All right, so the actual solution here is A equals 150 minus e to the negative 1 over 20, or over 200 t minus c. Hey, remember in class we used an exponent property? I want to use the exact same exponent property to make this look better, because I don't like the way that this looks right now. So A equals 150 minus e to the negative 1 over 200t times e to the negative c. I'm going to take a moment here to say that k is equal to e to the negative c. Oh, the lights just went out on me. That's nice. So if that's the case, then we got that A is equal to 150 minus k, so I'm going to put the k out in front, e to the negative 1 over 200t. That last part wasn't necessary, but I think it's going to be easier for me in just a moment, and you'll see why actually. Okay, so next step is I got to figure out what k is, or what was the C if you're going to leave it that way. So I need some more information. Well, the thing that helped me figure out if it was plus or minus is actually the exact same piece of info that can help me out with K. I know that at time 0, there was 20 kilograms of salt in this tank. So that's going to be the thing that's going to send me to my next step. So the formula I came up with was A equals 150 minus K e to the negative 1 over 200t. And I know that at time 0, the amount of salt in the tank is 20 kilograms. Cool. So negative 1 over 200 times 0 is 0. E to the 0 is 1. So that leaves me with that 20 equals 150 minus K, which means that K must be 130. So the specific solution for this is A equals 150 minus 130 e to the negative 1 over 200t. Awesome. Last step here is to answer the question. So this formula represents the amount of actual salt in the tank. Notes that it is always going to be less than 150. And as time goes on, as we go to infinity, we approach 150. So now we just need to find A of 30. So let's do it. 150 minus 130e to the negative 1 over 200 times 30. And this is where a calculator comes in handy. So let's see what we get here. So we got e to the negative 130 over 200. So that's about a 0.86-ish up there. So I'm going to multiply that by 130, which is about 111-ish. So we'll go 150 minus that answer, and that gets me 38.10796. So to finish it out, if we were round into 3 decimal places, as we should, there is 38.107 or 38.108 kilograms of salt at 30 minutes. All right, and there you have it. So that is the whole thing there. Let me sort of recap. So we start with defining some variables. It's always going to be rate in minus rate out. So we find those things. Typically, the rate out is what's going to be changing. The rate in will be something that's constant, typically, not always though. So once you find those, you write your differential equation, get everything to the opposite sides and integrate, and solve. Most of the time, just FYI, you're going to have a denominator that is like a 150 minus A or a 20 minus Y or whatever it is. So like keep in mind this idea of substitution or sort of compensating for that negative. So we solve. Again, you don't have to write it this way with the K instead of the C, but you'll notice that once I plugged in, this whole mess became a lot easier to deal with. You plug in 0, and then finding K was very simple. If you were over here and you had to plug in 0 for T and solve for C, it's messier. It's not the worst, but it's a bit messier. It's got some natural logs in it. So once you have the definite equation, you plug in your value you're interested in, solve, and write out a concluding sentence. So we're going to definitely get a lot more practice on this in class. So please take the little survey so that way I have your questions and I'm ready for them next class. And I'll see you all when I see you.